The information and pictures are from the internet, and the content is for reference only. Ozone hole. Source: ChatGPT. Ozone hole refers to the phenomenon of abnormal reduction in ozone layer content in the Earth's stratosphere, forming locally thinning areas. The ozone layer is mainly located at an altitude of about 15-30 kilometers, and is able to absorb and block most of the harmful ultraviolet rays emitted by the sun, especially UVB, protecting life on Earth. Formation causes. The main cause of the ozone hole is chlorine-containing and bromine-containing compounds such as chlorofluorocarbons, CFCs, and halogens emitted by human activities. Entering the stratosphere, these substances decompose under the action of ultraviolet light, releasing chlorine or bromine atoms, which destroy ozone molecules. Main area. The area over Antarctica is the most typical area of the ozone hole, with the most severe occurring in spring, September to November, each year. Ozone loss can also occur in the Arctic, but it is usually not as severe as in Antarctica. In danger. More UV rays reach the surface, increasing the risk of skin cancer, cataracts, and other diseases. Affects marine plankton and crops, damaging ecosystems. It may affect atmospheric circulation and climate systems. International response. The Montreal Protocol, adopted in 1987, restricts and phases out the production and use of ozone-depleting substances. After decades of efforts, scientists have observed that the ozone layer is slowly recovering, and it is expected that it may return to pre-1980 levels by the middle of this century. Source: Wikipedia. Ozone depletion, a phenomenon in which ozone in the stratosphere, ozone layer, above the Earth's atmosphere has been declining at a rate of 4% per decade since the 1970s. In some seasons in the polar regions, the rate of decline is more than 4% per decade, and even tropospheric ozone decreases in spring, forming the so-called ozone hole. The main cause of ozone depletion is the catalytic action of chloride and bromide on ozone decomposition, which are mainly derived from ground-released hydrochlorofluorocarbons, CFCs, under the trade name Freon. Because the ozone layer can block harmful ultraviolet rays, wavelength 270 to 315 nanometers, from entering the atmosphere, the depleted and thin or even whole ozone layer will lead to an increase in the number of patients with skin cancer, cataracts, and other diseases, and cause the extinction of some biological species, such as marine plankton, so the Montreal Protocol prohibits the production of some substances that can cause ozone depletion such as HCFCs. There are three types of oxygen allotropes in the ozone layer: oxygen atom, O, oxygen molecule, O2, and ozone, O3, which are photolyzed into two oxygen atoms after absorbing ultraviolet light with a wavelength of less than 240 nanometers, and each oxygen atom will combine with oxygen molecules to form ozone molecules. Ozone molecules absorb ultraviolet rays with wavelengths of 310 to 200 nanometers, and then decompose into an oxygen molecule and an oxygen atom, which eventually combine with the ozone molecule to form two oxygen molecules. O plus O3 to O2. Ozone will be catalyzed by some free radicals to form oxygen and disappear. The main free radicals are hydroxide, O, nitric oxide, NO, chlorine atoms, Cl, and bromine atoms, Br. These free radicals are naturally generated and artificially created, among which hydroxide groups and nitric oxide are mainly naturally produced, while chlorine atoms and bromine atoms are produced by human activities, mainly some man-made substances, such as fluorochlorocarbons and freons. Because they are relatively stable, they will not decompose after being released into the atmosphere, and will decompose under the action of ultraviolet rays after entering the stratosphere, becoming a free state. Ozone. Source: ChatGPT. Ozone, O, is a gas composed of 3 oxygen atoms and is an allotrope of oxygen, O. It is unevenly distributed in the atmosphere and has very important environmental and biological implications. Underscore 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 un. 1. Basic properties of ozone. Chemical formula: O. Color and smell: light blue gas with a special pungent odor, often smelled after thunderstorms. Stability: unstable at room temperature and easily decomposed into oxygen. Strong oxidation: stronger than oxygen, can sterilize, disinfect, and remove organic pollutants. Underscore 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 un. 2. Atmospheric ozone distribution. Ozone has two sites in the atmosphere, depending on the altitude at which it is located. Stratospheric ozone, about 15-30 km altitude. O. It forms an ozone layer that absorbs the sun's ultraviolet rays, especially UVB. O. Function: protect Earth organisms from UV rays. O. Good ozone. Tropospheric ozone, near the ground. O. It is produced by the reaction of nitrogen oxides, NOx, and volatile organic compounds, VOX, in automobile exhaust and industrial exhaust gases under sunlight. O function, it is an air pollutant that is harmful to the human respiratory system. O bad ozone. Underscore 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 un. 3 Main role. Environmental protection. Stratospheric ozone absorbs about 97–99% of ultraviolet radiation. Public health. Ozone layer deficiency, skin cancer, cataracts increase. Air quality indicators. Ground level ozone is a crucial component of the air pollution index. Industrial applications, used for water treatment, air purification, food preservation. Source, Wikipedia. Ozone, English, ozone, or trioxygen, chemical formula, O3, is a monoplasmic triatomic molecule of oxygen, an allotrope of oxygen, hydrogen dioxide, and a pale blue gas with a pungent taste at room temperature. The English name for ozone comes from the Greek neutral present participle ozeon, which means to smell. Ozone is mainly found in the ozone layer in the lower stratosphere 20 km from the Earth's surface, with a content of about 50 ppm, mainly produced by photolysis from ultraviolet radiation in sunlight to produce oxygen peroxide, and a small amount is produced by electrolysis of the phenomenon of electrical discharge, lightning, in the atmosphere. Ozone is a more active oxidant than oxygen, absorbing shortwave ultraviolet rays that are harmful to biological cells and genetic material, preventing them from reaching the surface. Ozone is a light blue gas that is slightly soluble in water and easily soluble in carbon tetrachloride or fluorocarbons and appears blue. Condenses into a dark blue liquid at -112 degrees Celsius. At temperatures below -193 degrees Celsius, ozone forms purple-black solids. Most people can smell something pungent similar to chlorine. Exposure to 0.1 to 1 ppm of ozone can cause headaches, burning eyes, and irritation of the respiratory tract. Even low concentrations of ozone in the air can damage organic materials such as rubber, plastic, and animal lung tissue. Ozone is diamagnetic, which means its electrons are all paired. Ozone has an isosceles triangle structure, containing a 3-center 4-electron delocalization pi bond, and the 3 oxygen atoms are located at the 3 vertices of the triangle, with the top angle of 116.79 degrees, a density about 1.5 times that of oxygen, and its boiling and freezing points are higher than oxygen. Ozone appears blue-purple in its liquid state and purple in its solid state. It differs from oxygen, with a high concentration of ozone zones that give it a noticeably disgusting odor. But the low concentration of ozone smells like the fresh air you smell when you go out after rain, which is very pleasant. Ozone is highly reactive, easily decomposed, and very unstable, and will gradually decompose into oxygen at room temperature. Ozone is more active than oxygen, with a specific gravity of 1.7 times that of ordinary air. Ozone is accelerated by light, heat, moisture, metals, metal oxides, and other catalysts to break down into oxygen. It is insoluble in liquid oxygen, etc. It has strong oxidizing properties, and can oxidize silver to silver oxide and lead sulfide to lead sulfate at room temperature. Ozone can fade many organic pigments, is very damaging to rubber and fibers, and easily oxidizes organic unsaturated compounds. Ozone is extremely stable in ice, with a half-life of 2,000 years. Ozone layer. Source, ChatGPT. The ozone layer is an area of the Earth's atmosphere with relatively high concentrations of ozone, O, in the stratosphere, about 1530 km altitude. Although ozone is only a few parts per billion of the entire atmosphere, it has a crucial role in protecting life. Underscore 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 un. 1 Formation. The ozone layer is formed primarily through photochemical reactions of oxygen. 1 High-energy ultraviolet light breaks down oxygen, O, into individual oxygen atoms, O. O2 UVO plus OO_2 / ecritero UVO and OO2 UVO and O. 2 individual oxygen atoms combine with oxygen molecules to form ozone, O. O plus O2O3 O plus O_2 / ritero O_3 O plus O2O3. Ozone itself can also be broken down by ultraviolet rays, creating a dynamic equilibrium. Underscore 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 un. 2 Function. Absorbing UV rays. The ozone layer absorbs most of UVC and large amounts of UVB, preventing harmful radiation from reaching the surface. Life protection barrier. Reduces risks such as skin cancer, cataracts, and genetic mutations. Climate regulation. Ozone absorbs solar energy, warming the stratosphere and affecting atmospheric circulation. underscore 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 un. 3. Destruction of the ozone layer. Human factors, mainly from chlorofluorocarbons, CFCs, halons, and other substances, which decompose and release chlorine, bromine radicals and catalyze the decomposition of ozone. Natural factors, such as volcanic eruptions, solar activity, etc., may also affect ozone concentration. Typical phenomenon: the ozone hole over Antarctica is most severe in the southern hemisphere in spring. Underscore 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 un. 4. International Protection Action. 1987 Montreal Protocol, globally restrict the production and use of ozone-depleting substances such as CFCs. Amendments and enhancements, subsequent restrictions on hydrofluorocarbons, HFCs, were added. Effects. Scientific monitoring suggests that the ozone layer is gradually recovering, and it is expected that the mid-21st century will return to pre-1980 levels. Source: Wikipedia. The ozone layer refers to the part of the Earth's atmosphere in the stratosphere where ozone concentrations are relatively high. The ozone layer is densest over the tropics near the equator and lowest over the north and south poles, and if compressed into the troposphere, it is only a few millimeters thick and even forms cavities. The ozone layer can absorb shortwave ultraviolet rays that shield sunlight, reduce the ionizing radiation that reaches the surface harmful to biological cells and genetic material, and can also prevent the permanent loss of hydrogen from the free atmosphere after surface water is subjected to ultraviolet photolysis, which is extremely important for the protection of the Earth's biosphere. The formation of ozone in the atmosphere is mainly due to the absorption of ultraviolet rays by oxygen molecules to obtain high energy, which then decomposes into 2 oxygen atoms, each of which merges with O2 without photodecomposition. The ozone molecule is unstable, and after ultraviolet irradiation, it is divided into oxygen molecules O2 and oxygen atoms, forming a continuous process of ozone and oxygen cycle, thus producing the ozone layer. Fully depletes the ozone layer. Source: ChatGPT. Freon, commonly known as chlorofluorocarbons, CFCs, has been widely used as a refrigerant, foaming agent, and propellant. They are ground-stable, non-toxic, and odorless, but precisely because they are so stable they can exist in the atmosphere for decades to hundreds of years, eventually entering the stratosphere and wreaking havoc on the ozone layer. Underscore 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 un. 1. Mechanisms that destroy the ozone layer. 1. Rise to the stratosphere. OCFCs do not break down easily and can slowly diffuse into the stratosphere. 2. Ultraviolet degradation CFCs. High-energy UV light interrupts CFCs, releasing chlorine atoms, Cl, or bromine atoms, Br. For example, CFCl3 UVCFCl2 plus ClCFCl_3 \ecritero UVCFCl_2 plus ClCFCl3 UVCFCl2 plus Cl. 3. Chlorine atoms catalyze the destruction of ozone. A chlorine atom can destroy thousands of ozone molecules in a row because it cycles in Cl plus O3 ClO plus O2 Cl and O_3 \ritero ClO and O_2 Cl plus O3 ClO plus O2 Clo and O Cl and O2 Clo and O \ritero Cl and O_2 Clo and O Cl and O2. Result: O is converted to O, and ozone concentration decreases. Underscore 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 un. 2. Impact. Ozone hole, especially in the Antarctic spring, low temperatures and polar stratospheric clouds promote reactions, causing ozone concentrations to plummet. Health risks: UV enhancement, skin cancer, cataracts, immune system damage. Ecological damage: affects plankton, crops, and disrupts the food chain. Underscore 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 un. 3. International response. 1987 Montreal Protocol, global phasing out of CFCs, halons, and other substances. Alternatives: HFCs, HCFCs, etc., although they do not destroy the ozone layer, are some potent greenhouse gases and are currently being gradually restricted. Effect: the latest monitoring shows that the ozone layer is recovering and is expected to approach pre-1980 levels by the middle of the 21st century. Source: Wikipedia. Freon is a registered trademark of several halogen carbon products manufactured by Chemours, Inc. These substances are usually stable, non-flammable, moderately toxic gases or liquids that are often used as refrigerants or aerosol push sprays. Early freons contain chlorofluorocarbons, CFCs, that tend to cause ozone layer cavities, such as difluoromonochloromethane, and now improved refrigerants have replaced chlorine with fluorine to mitigate the impact of chlorine on ozone layer destruction. Not all refrigerants are called freon, only R12, R13B1, R22, R502, and R503 made by Chemours are labeled as freon. Freon has become a common term and usually refers to any fluorocarbon refrigerant. Some scholars believe that the ozone layer is destroyed near chlorine, fluorine, and bromine atoms. These elements are found in very stable chlorofluorocarbons, CF2Cl2, such as freon, and a commonly used gasoline additive. These gas molecules rise to the stratosphere and, after ultraviolet exposure, decompose into various single-element gases that destroy ozone. These gases are heavier than air and eventually fall to the surface of the Earth, react with organic matter and be absorbed. But in the stratosphere, a lot of ozone has been destroyed. Chlorine is the most destructive, destroying 100,000 times its ozone. In 1973, Mexican chemist Mario Molina first proposed that freon has an effect on the ozone layer. Freon is a CFC that has been used as a refrigerant in refrigerators and air conditioners for over 20 years. However, at that time, no scholars tested the thickness of the ozone layer, and there was not much ozone layer research, and governments did not care. The ozone hole was gradually discovered during Antarctic research. These studies are measured together on the ground and in the air, and are measured by countries working together. The most famous is a large-scale study conducted in Punta Arenas, Chile, on behalf of 19 organizations in 4 countries in 1987, the Airborne Antarctic Ozone Experiment. This experiment showed that the ozone hole reached the largest size in history in 1987, attracting the attention of scientific and political circles. Scholars who also hold the view of freon breaking the ozone layer believe that the reason why there is an ozone layer hole over Antarctica is due to the extreme cold in the area. They believe that when the surface temperature of particles in the cloud is below -73 degrees Celsius, any form of chlorine conversion will undergo a chemical reaction to convert it into reactive chlorine. When Antarctica is in the warm season, November-March, chlorine compounds in the ozone layer over Antarctica are only affected by the sun's ultraviolet radiation and decompose slowly. However, when entering the cold winter, April-October, the temperature can reach -88.3 degrees Celsius, and the cold particles in the clouds become the catalyst for the chemical reaction that releases active chlorine, which further destroys the ozone over Antarctica, resulting in an ozone layer hole. The smell after a thunderstorm. Source: ChatGPT. One of the fresh and pungent odors that is often smelled after thunderstorms is ozone. One formation causes lightning action. During thunderstorms, lightning discharges generate extremely high temperatures and energy, which can crack oxygen, in the air into individual oxygen atoms, These oxygen atoms then combine with oxygen to form ozone. O2 lightning 200_2 lightning 2002 lightning 200 plus O2030 plus O_2 plus O30 Discharge effect. Not only lightning, but also short circuits in wires, copiers, and high voltage transmission equipment can also smell similar ozone odors. Two odor characteristics. Low concentration, feels similar to grassy smell or fresh air. Slightly higher concentration, it will have a pungent odor. Three health effects. A small amount, the ozone concentration in the air after a thunderstorm is usually not high harmless, but makes the air feel fresh. High concentration, it can irritate the respiratory tract and eyes, causing coughing, throat discomfort, and long-term exposure may damage the lungs. Source: AI Summary. There are two main types of smells after thunderstorms. One is ozone generated by lightning and the atmosphere, bringing a fresh and slightly sweet smell. The other is petrichor, aquifer oil, released by rainwater washing away the soil, which contains pterosmine, earthy smell, from the soil and terpenoids released by plants, grassy smell, filling the air with unique soil and plant aromas. Main sources of odor. Ozone. Lightning breaks down oxygen in the air to form ozone, which may also bring ozone from the upper stratosphere to the ground. Ozone has a fresh, slightly sweet or bleached scent that makes the air feel cleaner. Petrichor. This is the smell produced when rain falls on dry land, derived from the Greek words for stone and blood of God. Geosmone, a compound produced by actinomycetes in the soil and is the main component of aquifer oil, which produces an earthy odor. Plant essential oils, terpenes. During the dry season, plants secrete oils that are released into the air along with other chemicals in the soil when rain falls. Hydrogen peroxide and negative ions. Rainwater can also produce hydrogen peroxide, and the increase in negative ions can also improve the freshness of the air. How the smell is produced. Interaction with air. Lightning pushes ozone from high altitudes to the ground and breaks down oxygen to form ozone. Interaction with the ground. Raindrops wash away geosmin and vegetable oils from the soil, while rainwater also washes away dust from the air, making the air cleaner. Plant release. When rainwater hits the leaves or rain washes over the surface of dry plants, they release aromatic substances secreted by the plants themselves. Ultraviolet light. Source: ChatGPT. Ultraviolet, UV, is an electromagnetic wave with a wavelength shorter than visible light and longer than X-rays, about 100–400 nanometers, nm, and invisible to the human eye. It is an important component of solar radiation. One classification of ultraviolet light. Commonly used international division methods. UVA 320–400 nm. O. The wavelength is the longest and the energy is the lowest. O. It has strong penetrating power and can reach the dermis layer of the skin. O. Function: tanning the skin and accelerating aging. UVB 280–320 nm. O. The energy is higher, most of it is absorbed by the ozone layer, and some of it can still reach the surface. O. Function: sunburn the skin, increase the risk of skin cancer, and promote vitamin D synthesis. UVC 100–280 nm. O. The energy is the highest, but almost all of it is absorbed by the ozone layer and the atmosphere. O. It can be produced manually, such as disinfection lamps, for sterilization and disinfection. Two source. Natural sources, mainly from solar radiation. Artificial sources, UV lamps, welding arcs, black lights, medical and beauty equipment. Three impact on organisms and the environment. Positive effects. O. Sterilization and disinfection, UVC. O. Promotes the synthesis of vitamin D, UVB, in the human body. Negative effects. O. Skin, tanning, sunburn, photoaging, increasing the risk of skin cancer. O. Eyes, ultraviolet keratitis, cataracts. O. Environment, excessive UV rays can disrupt the ecological balance. Four protection methods. Use sunscreen, choose the right SPF and PA values. Wear sun protection clothing, hats, and sunglasses. Avoid prolonged exposure to the sun during the strongest UV hours, 10 am 3 pm. Source: Wikipedia. Ultraviolet, English, ultraviolet, abbreviated as UV, is an electromagnetic wave with a wavelength between 10 nm and 400 nm, its wavelength is shorter than visible light but longer than X-rays. Sunlight contains some ultraviolet rays, and arcs, mercury lamps, and black lights also emit ultraviolet rays. Although ultraviolet light is not ionizing radiation, it can still trigger chemical reactions and fluoresce some substances. UV radiation less than 200 nanometers will be strongly absorbed by air, so it is called vacuum ultraviolet rays. Ultraviolet A, UV longer wavelength, between 320–400 nanometers, can penetrate clouds, glass into indoor and car interiors, and can penetrate into the dermis of the skin, causing tanning. UVA can be further subdivided into UVA 2, 320–340 nm, and UVA 1, 340–400 nm. UVA 1 has the strongest penetrating power, reaching the dermis to tan the skin, which is the most harmful to the skin, but it is also the most easily ignored, especially in non-summer. Although the UVA 1 intensity is weak, it still exists, and will cause skin damage due to the amount accumulated over time. UVA 2, like UVB, can reach the epidermis of the skin, causing sunburn, redness, and pain, solar keratosis, and loss of transparency. Ultraviolet B, UVB. The wavelength is centered, with a wavelength between 280–320 nanometers, which will be absorbed by the ozone layer, causing sunburn and skin redness, swelling, heat and pain. Ultraviolet C, UVC. The wavelength is between 100–280 nanometers, but because the wavelength below 200 nanometers is vacuum ultraviolet rays, it can be absorbed by air, so ultraviolet C, UVC, can pass through the atmosphere with wavelengths between 200 to 80 nanometers, and the shorter the wavelength, the more dangerous it is, but because the ozone layer can completely block UVC, all living things on Earth will not be harmed by UVC. The ultraviolet rays emitted by the sun include UVA, UVB, and UVC bands. The Earth's ozone layer blocks 97 to 99% of ultraviolet radiation penetrating the atmosphere. 98.7% of the ultraviolet rays that reach the Earth's surface are requested from UVA sources. UVC and higher energy radiation contribute to the formation of ozone and form the ozone layer. Hotter stars emit more ultraviolet light than the sun. The thermal energy of the star R136A1 is 4.57 eV, which falls in the near ultraviolet range. The transmittance of ordinary window glass to wavelengths above 340 nanometers, UVA, is about 90%, but for wavelengths below 340 nanometers, UVB, 90% will be blocked. The wavelength of vacuum ultraviolet light starts at 200 nanometers and can of course be passed through in a vacuum, hence the name, but is absorbed by oxygen molecules in the air and is therefore impenetrable. Pure nitrogen, about 10 ppm lower than oxygen, is penetrating in the 150-200 nm band, which is very meaningful for semiconductor processes because wavelengths shorter than 200 nm are always used in the process. Personnel and equipment working in an oxygen-free environment do not have to endure the pressure difference caused by working in a vacuum. Other scientific instruments that work in this spectral range, such as circularly polarized dichroism spectrometers, are also often cleaned with nitrogen. The properties of extreme ultraviolet light are used to physically convert the interaction of matter. Wavelengths longer than 30 nanometers mainly chemically interact with the valence electrons of the substance, and shorter wavelengths interact with the electrons and nuclei of the inner shell. The EUV/XUV spectral longwave end is set to a significant He end line of 30.4 nanometers. Most known substances absorb XUV strongly, but it can also be made into multi-layer optics, which can reflect about 50% of perpendicular incident XUV radiation. This technology was first used in the 1990s on NIXT and MISTA sounding rockets to create telescopes that produce solar images. Current examples include SOHO/EIT and TRACE, and nanolithography devices, traces and devices printed on very small-scale microchips. Skin cancer. Source: ChatGPT. Skin cancer is one of the most common types of cancer, which refers to abnormal proliferation and malignant transformation of skin cells. It is often closely related to UV exposure, but also to genetics, environment, immune status, and other factors. One common types. Skin cancer is divided into three main categories. BCC, basal cell carcinoma. O the most common, about 70-80%. O grows slowly, rarely transfers. O commonly seen on sun-exposed areas such as the face, ears, and neck. SCC, squamous cell carcinoma. O subcommon, accounting for about 20%. O they grow faster than BCCs and have a certain risk of metastasis. O it often occurs on skin or chronic wounds that have been exposed to the sun for a long time. Melanoma. O although the incidence is low, about 1-5%, it is the most dangerous. O originating from melanocytes in the skin, they are easily metastasized. O it is closely related to intense, intermittent UV exposure, sunburn. Two risk factors. Ultraviolet, UV, light, the most important factor, especially UVB. Light skin tone, lacks melanin protection. Genetic factors, family history of skin cancer. Immunosuppression, organ transplant patients, those taking immunosuppressants for a long time are at increased risk. Other, chronic wounds, chemical exposure, such as arsenic, radiation exposure. Three warning signs, of blah, used to identify melanoma. A. Asymmetry. Asymmetry, one half of the mole is not the same as the other half. B. Border jagged and blurry edges. C. Color available in various colors, black, brown, red, white. D. Diameter, large diameter, greater than 6 mm, pencil eraser size. E. Evolving, changes, moles change in a short period of time, getting bigger, bleeding, itching. For prevention. Avoid strong sun exposure, especially at noon. Use a broad-spectrum sunscreen, SPF 30+, PA+++. Wear protective clothing, hats, and sunglasses. Regularly self-examine your skin and seek medical attention as soon as possible if you find abnormal moles or spots. Underscore 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 un. 5. Treatment. Surgical excision, the preferred method for most skin cancers. Radiotherapy/chemotherapy, used for inoperable or metastatic cases. Immunotherapy/targeted therapy, especially for advanced melanoma. Source: Wikipedia. Skin cancer is a type of cancer that grows on the skin and develops from abnormal cells that may even invade and spread to different parts of the body. Since skin cancer often develops in the epidermis and tumors are often clearly visible, skin cancer can be detected at an early stage most of the time. Unlike most cancers, including lung, pancreatic, and stomach cancers, the number of deaths from skin cancer is small. Skin cancer is the most common cancer, surpassing lung cancer, breast, colorectal cancer, and prostate cancer. The 3 most common types of skin cancer are basal cell carcinoma, BCC, squamous cell carcinoma, SCC, and melanoma. The first 2 and less common skin cancers are called non-melanoma skin cancers, NMSC. Basal cell carcinoma grows slowly and may destroy surrounding tissues, but is less likely to metastasize distantly or cause death. Usually painless protrusions appear on the skin, shiny on the surface with small blood vessels, or ulcers at the protrusions. Squamous cell carcinoma is more likely to metastasize than basal cell carcinoma, usually presenting as a hard lump with a squamous epidermis, but it may also manifest as an ulcer. Compared with basal cell carcinoma and squamous cell carcinoma, melanoma is rarer, but melanoma is the most malignant among them, and possible signs include changes in the size, shape, and color of the mole, irregular edges of the mole, uneven color, and may itch or bleed. More than 90% of skin cancer cases are caused by exposure to UV rays from the sun, and such exposure increases the risk of developing the 3 main skin cancers mentioned above. The thinning of the ozone layer may be responsible for the increased exposure. Tanning machines are another common source of UV rays in recent years. In the case of melanoma and basal cell carcinoma, childhood exposure is particularly harmful. In the case of squamous cell carcinoma, the total exposure is more critical than the period of exposure. 2 to 30% of melanomas develop from moles. People with fairer skin, people with poor immune systems, such as those receiving certain medications, people with human immunodeficiency virus infection, or people with AIDS are at higher risk of developing the disease. Skin cancer must be diagnosed by biopsy. Reducing UV exposure and using sunscreen oil are the most effective ways to prevent melanoma and squamous cell carcinoma, but the impact of sunscreen oil on basal cell carcinoma is still unclear. Non-melanoma skin cancers are usually curable. Treatment is mainly through surgical resection, as well as less common radiation therapy or topical drugs such as fluorouracil. Melanoma treatment involves a combination of surgery, chemotherapy, radiation therapy, and targeted therapy. For those with distant metastases, palliative care may help improve quality of life. The survival rate for melanoma is higher than any cancer, with a 5-year survival rate of 86% in the UK and 90% in the US. Skin cancer is the most common form of cancer, accounting for 40% of all cancers worldwide. It is especially common in people with lighter skin tones. The most common type is non-melanoma, which affects about 2 to 3 million people each year. This is a rough estimate, as the more granular data is not continuously tracked. Among non-melanomas, about 80% are basal cell carcinomas, and 20% of them are squamous cell carcinomas. In the United Kingdom, as of 2009, an average of 9,500 people suffered from the disease and 2,300 died each year. Melanoma is one of the most common cancers in people aged 20 to 30, mostly caused by prolonged sun exposure. These 2 cancers rarely cause deaths, accounting for less than 0.1% of all cancer deaths in the United States. Global cases show that there were 23.2 new melanoma cases in 2012, and melanoma caused a total of 5.5 deaths that year. Australia and New Zealand have the highest melanoma mortality rates in the world. The incidence of these 3 types of skin cancer has increased over the past 20 to 40 years, especially in predominantly white countries. Diseases caused by ozone layer reduction. Source: ChatGPT. The main role of the ozone layer is to absorb the sun's ultraviolet rays, especially UVB. When the ozone layer decreases, thinning or ozone holes appear, more UV rays reach the surface, causing harm to human health and ecology. Underscore 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 un. 1 Human diseases and health effects. Skin diseases. Skin cancer, especially melanoma, squamous cell carcinoma. UV rays cause DNA damage and mutations. Sunburn, acute inflammation of the skin, erythema, blisters. Premature skin aging, collagen is damaged, wrinkles and pigmentation appear. Eye disease. O cataracts, UV rays damage the lens, causing cloudiness. O keratitis/photokeratitis, caused by strong ultraviolet radiation in a short period of time. O retinal damage, long-term high doses of ultraviolet light can harm vision. Immune system. O excessive UV rays can suppress immune function, making the body more susceptible to diseases or reducing the effectiveness of vaccines. Two environmental and indirect hazards. Aquatic ecology, UV light can kill plankton, affecting the marine food chain. Reduced crop yield, UV rays damage chloroplasts and reduce photosynthesis. Animal health, skin and eye diseases can also occur in domestic and wild animals. Source: AI Summary. The main health effects of ozone layer reduction include increased rates of skin cancer, including melanoma, skin lesions, and cataracts, as it causes the ground to receive more harmful UV radiation. Additionally, excessive UV radiation can affect immune system function, damage DNA molecules, and cause widespread harm to ecosystems. Effects on human health. Skin cancer. The ozone layer decreases and allows more UVB radiation to reach the Earth's surface, damaging the DNA of skin cells and increasing the risk of developing squamous cell carcinoma, basal cell carcinoma, and malignant melanoma. Cataracts. Prolonged exposure to sunlight and excessive UV radiation can increase the incidence of cataracts. Immune system. Excess UV radiation can damage the body's immune system, making it more susceptible to disease. Other effects. Ecosystems. Enhanced UV radiation can cause harm to plants and marine life, affecting their growth and reproduction. Food chains. Impacts on aquatic ecosystems and crops can threaten global food supplies. Environmental impact. Ozone layer depletion exacerbates climate change and affects biogeochemical cycles in the atmosphere. The ozone layer resists ultraviolet rays. Source: ChatGPT. The ozone layer is the protective shield of the Earth's atmosphere, which effectively absorbs and blocks the sun's ultraviolet, UV, rays, especially those harmful to living things. One. How the ozone layer absorbs ultraviolet rays. Ozone, O, molecules are very sensitive to ultraviolet light and can react photochemically with ultraviolet light at different wavelengths. UVC 100280 nm. O, almost 100% of it is absorbed by the ozone layer and oxygen and does not reach the surface. Oh, this is the most dangerous UV ray that kills cells in an instant. UVB 280320 nm. Oh, about 90% is absorbed by the ozone layer, and some of it still reaches the surface. Oh, may cause sunburn, skin cancer, cataracts, but also promote vitamin D synthesis. UVA 320400 nm. Oh, it is almost not absorbed by ozone and mostly reaches the surface. Oh, it has strong penetrating power and can penetrate deep into the dermis of the skin, causing skin aging and melanin precipitation. Two protective mechanisms. The existence of the ozone layer is like setting up a light filter in the outer layer of the Earth. 1. Absorbs high-energy UV, prevents direct DNA damage. 2. Protects humans, animals, and plants from excessive radiation. 3. Maintain the ecological balance of the Earth, e.g., plankton are not killed by excessive ultraviolet rays. Three. If the ozone layer decreases. UVB increases skin cancer, cataracts, decreased immunity. Ecosystem damage, reduced crop yields and disruption of marine food chains. Source: AI Summary. The ozone layer is located in the stratosphere, about 10 to 50 kilometers above the surface, and absorbs most of the shortwave ultraviolet rays, UVB and UVC, that are harmful to living organisms and sunlight. It's like the Earth's protective umbrella, shielding surface organisms from diseases like skin cancer, cataracts, and more by absorbing UV rays and converting them into heat energy. Mechanism of action of the ozone layer. Absorbing UV rays. Ozone molecules absorb ultraviolet rays from the sun and break down into oxygen atoms. Release heat energy. The absorbed UV energy is converted into heat energy, which heats the atmosphere in the stratosphere. Dynamic equilibrium. The decomposed oxygen atoms quickly combine with atmospheric oxygen to form new ozone molecules and maintain the dynamic balance of the ozone layer. Types and effects of ultraviolet rays. Scientists divide ultraviolet light into 3 zones according to wavelength. UVA, 315-400 nm, can reach the surface but does little damage to surface organisms. UVB, 280-315 nm, can reach the surface and cause serious harm to living organisms, such as increasing the risk of skin cancer and cataracts. UVC, less than 280 nm, high energy, but almost all of it is absorbed by ozone and oxygen in the atmosphere and does not reach the Earth's surface. The importance and protection of the ozone layer. Protecting Earth's life, the ozone layer acts as a protective umbrella for Earth's organisms, providing a line of life defense for surface organisms from intense UV rays. International conservation action. The discovery of the Antarctic ozone hole in 1985 has attracted the attention of the scientific community and the international community. The Montreal Protocol, signed in 1987, aims to phase out ozone-depleting substances and protect the planet's ecosystems. Atmosphere. Source: ChatGPT. The atmosphere is a layered structure composed of gases on the outer edge of the Earth, extending from the surface to hundreds of kilometers or more, like a gas shell protecting life on Earth. One composition of the atmosphere. Key ingredients: clean air, near sea level. ON 78%. O oxygen, O, 21%. OAR 0.93%. O carbon dioxide, CO, 0.04%, varies with human activities. O other trace gases, water vapor, neon, helium, methane, ozone, etc. Two stratification of the atmosphere, by altitude and temperature. 1 troposphere, 012 km. O contains most of the water vapor and clouds, and the weather phenomenon occurs. O the higher the altitude, the lower the temperature. 2 stratospheric, 1250 km. O the ozone layer is located and can absorb ultraviolet rays. O as altitude increases, the temperature increases. 3 middle layer, 50-85 km. O the temperature decreases with altitude, reaching around -90 degrees Celsius. O meteors often burn here. 4 thermosphere, 85-600 km. O the air is extremely thin, and the temperature can reach thousands of degrees C. O in the area where the aurora appears, there is also the orbit of the International Space Station, about 400 kilometers. 5 dissipative layer, greater than 600 km. O the transition zone with outer space, mainly hydrogen and helium, gradually escaped into the universe. Three functions of the atmosphere. Protective effect. O absorbs ultraviolet rays and part of the cosmic rays, ozone layer. O attenuates meteor impact, burns out in the middle layer. Regulate the climate. O maintain the greenhouse effect and make the planet habitable. Supporting life. O it provides oxygen for breathing and carbon dioxide for biological circulation. Source: Wikipedia. The Earth's atmosphere, usually simply referred to as the atmosphere, or atmosphere, is a layer of gas mixture that gathers on the outside of the Earth's planetary surface, land and ocean, due to the gravitational constraints of the Earth, and there are also indefinite amounts of liquid aerosols and solid particulate matter suspended in it to form clouds, fog, and haze and other weather phenomena. The Earth's atmosphere can be divided into 5 regions: troposphere, stratosphere, mesosphere, thermosphere, the main body of the ionosphere, and outer atmosphere, with no exact upper boundary, and there are still thin gases and elementary particles at an altitude of 2,000 to 16,000 kilometers, 1,200 to 9,900 miles, above the surface. Small amounts of gas are also present in caves, soils, and some rock formations, and can also be considered as a component of the atmosphere. The gaseous part of the Earth's atmosphere is collectively known as air, and its main components today are nitrogen, molarity about 78.1%, oxygen, 20.8%, argon, 0.934%, water vapor, 0.3%, humidity will change due to local temperature and pressure fluctuations, carbon dioxide, 0.04%, and trace gases, such as helium, methane, krypton, etc., with a proportion of less than 0.03%. The total mass of the Earth's atmospheric gases is about 5.15 times 1018 kilograms, 5.15 times 1015 metric tons, equivalent to 0.86 ppm of the Earth's total mass, due to gravity, almost all of which is concentrated under the thermosphere 100 kilometers, 62 miles, above the ground, of which 99% is within 25 to 30 kilometers, 16 to 19 miles, below. The high density of the Earth's atmosphere compared to other celestial atmospheres makes it quite impressive, with sea level experiencing air pressure of up to 11 metric tons, 24,000 pounds, per square meter, and the mass of air per cubic meter can reach as much as 1.29 kilograms, 2.8 pounds. As the outermost part of the Earth's surface, the atmosphere can reduce the direct exposure intensity of solar radiation to the Earth's surface, especially the ozone layer can shield a large part of the ionizing radiation of high-frequency ultraviolet rays, all UVC and most UVB, and the greenhouse gases in it can also store heat to reduce the occurrence of extreme temperature differences between day and night. At the same time, the atmosphere can also physically bounce off or burn away some smaller objects that enter, reducing the probability of catastrophic impact events. The chemical composition of the atmosphere and the radiation, temperature, and physical buffers it provides to the surface are indispensable for the survival of organisms on Earth and the continuation of ecosystems, so the state of the atmosphere is a key indicator of planetary habitability. Climate change caused by changes in the state of the atmosphere is also the main cause of each cluster extinction, radiation, and succession of the biosphere, and is a major driver of biological evolution on Earth. The early Earth's atmosphere was completely different from today's atmosphere and was rich in volcanic eruption gases such as carbon dioxide. Part of the Earth's atmosphere may originate outside the solar system. The atmosphere now contains only a very small amount of carbon dioxide and is rich in oxygen. The reason for this change is that the microorganism inhales carbon dioxide and expels oxygen in an early life form. These microorganisms are collectively called blue-green algae and rely on photosynthesis to make energy, and they are very similar to those early oxygen-making organisms. The vertical structure of the atmosphere can be roughly divided into troposphere, stratosphere, mesosphere, thermosphere, and outer atmosphere. Troposphere. The atmosphere closest to the ground is called the troposphere, which includes the atmospheric boundary layer and the free atmosphere, with an average height of about 10 kilometers. The tropospheric height varies with latitude, with a maximum of about 15 kilometers at the equator and a minimum of about 8 kilometers at the polar regions. As the name suggests, the troposphere is the area with the most vigorous convection and where weather phenomena occur. About 80% of the water vapor in the atmosphere is present in the troposphere, so it is also the most frequent area for evaporation, clouds, and rain. On average, tropospheric temperatures decrease with altitude, with a decrease of about 0.6 degrees Celsius for every 100 meters of rise. Stratosphere. It contains ozone and has the function of absorbing ultraviolet rays, protecting the survival of all living things on Earth and the surface from the deadly attack of strong ultraviolet rays in the Sun, also known as the stratosphere. Because the ozone layer inside the stratosphere has the function of absorbing solar radiation, the temperature in this layer increases with altitude. Mesosphere. The main components of this layer are ozone, oxygen, carbon dioxide, and nitrogen oxides, which are products caused by photochemical reactions, so they are also called actinic layers. The temperature decreases with altitude. Warming layer. Also known as the hot air layer, the air is extremely thin and there are a lot of ions. The temperature is quite high and increases with altitude. Extraterrestrial layer. The starting point of outer space contains two of the lightest gases in the elements, hydrogen, H, and helium, He. Mario Molina. Source, ChatGPT. Mario Molina, 1943-2020, was a chemist of Mexican descent who is best known for his work on the mechanisms of chlorofluorocarbons, CFCs, on the destruction of the ozone layer. One biography. Birthplace, Mexico City, 1943. Education. O Bachelor of Chemistry from the National Autonomous University of Mexico. O Ph.D., University of California, Berkeley, USA. Occupation, chemist, professor, later taught at the University of California, San Diego, and MIT. Two scientific achievement. In 1985, he married Frank S.F. Sherwood. Rowland published a paper pointing out that CFCs, commonly known as folians, release chlorine atoms after entering the stratosphere, which catalyzes the destruction of ozone molecules. This discovery garnered global attention and directly led to the signing of the Montreal Protocol in 1987, which restricted the use of ozone-depleting substances. As a result, he is known as a pioneer in protecting the ozone layer. Three awards and honors. 1995 Nobel Prize in Chemistry, shared with Rowland, Paul Crutzen. In recognition of their contributions to ozonation science and the mechanisms of ozone layer destruction. He has won many international scientific awards and environmental protection honors. Underscore 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 on. 4. Social impact. Raise global awareness of ozone layer depletion and environmental protection. Promote international policy and environmental science research to strengthen human ability to deal with global environmental problems. Source: Wikipedia. José Mario Molina Pascual y Henríquez, Spanish, José Mario Molina Pascual y Henríquez, March 19, 1943 – October 7, 2020, was born in Mexico City, Mexico, a chemist who was one of the main figures in the discovery of the Antarctic ozone hole. He successfully explained the mechanism by which chlorofluorocarbons, CFCs, destroy the Earth's ozone layer, and was the first Mexican to win the Nobel Prize in Science with Frank Sherwood Rowland and Paul Crutzen for their research work on atmospheric chemistry, especially the formation and decomposition of ozone. Frank Rowland. Source: ChatGPT. Frank SF. Sherwood Rowland, 1927–2012, was an American chemist known for his research on the chemical mechanisms by which chlorofluorocarbons, CFCs, destroy the ozone layer. Underscore 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 on. 1. Biography. Birthplace: California, USA, 1927. Education: PhD in chemistry from the University of California, Berkeley. Occupation: Professor of Chemistry at the University of California, Irvine. Underscore 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 on. 2. Scientific achievement. In 1985, he married Mario M. Molina. Collaborated. He proposed the theory that CFCs rise to the stratosphere and then decompose, releasing chlorine atoms and catalyzing ozone decomposition. Uncover the hazards of human refrigerants and aerosols to the ozone layer. Important impact. The results of the study led to the signing of the Montreal Protocol in 1987. This is the first classic case of the international community taking action on a global environmental problem. Underscore 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 on. 3. Awards and honors. 1995 Nobel Prize in Chemistry, shared with Mario Molina, Paul Crutzen. Recognized pioneering research into the mechanisms of ozone layer destruction. He has also received several scientific awards for his contributions to environmental protection and chemistry education. Underscore 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 on. 4. Social impact. Raise global awareness of the impact of human activities on the atmosphere. Promoting international policy and scientific monitoring has become an important milestone in environmental chemistry research. Source: Wikipedia. Frank Sherwood Rowland, June 28, 1927 – March 10, 2012, was an American environmental chemist who won the 1995 Nobel Prize in Chemistry with Mario Molina and Paul Crutzen for discovering the mechanism of destruction of stratospheric ozone by chlorofluorocarbons, and was a professor of chemistry at the University of California, Irvine. His research focuses on atmospheric chemistry and chemical reaction kinetics. Folion enters the stratosphere, HCFC and ozone layer destruction. Source: ChatGPT. Freon, or chlorofluorocarbons, CFCs, can destroy the ozone layer when they enter the stratosphere. Underscore 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 on. 1. Characteristics of CFCs. On the surface, chemically stable, non-toxic, odorless, widely used as refrigerants, blowing agents, aerosols. High stability, can stay in the atmosphere for a long time, gradually rising to the stratosphere, about 15–30 km. Underscore 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 on. 2. Mechanism of ozone destruction. 1. Rise to the stratosphere. CFCs are difficult to break down on the ground or in the troposphere, so they float into the stratosphere. 2. Ultraviolet decomposition. Under high altitude ultraviolet radiation, CFC molecules are interrupted, releasing chlorine atoms, Cl. CFCl3 UVCFCl2 plus Cl CFCl underscore 3 backslash ecritero UVCFCl underscore 2 plus Cl CFCl3 UVCFCl2 plus Cl. 3 chlorine atoms catalyze the decomposition of ozone. O-chlorine atoms react with ozone molecules, destroying ozone to produce oxygen. Cl plus O3 ClO plus O2 Cl and O_3 backslash right arrow ClO and O_2 Cl plus O3 ClO plus O2 Cl and OCl and O2 Cl and O backslash right arrow Cl and O_2 Cl and OCl and O2. A single chlorine atom can cycle and destroy tens of thousands of ozone molecules. For result, stratospheric ozone concentrations decrease, the ozone layer thins, ultraviolet, UVB, increases reaching the surface. Underscore 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 un. 3 consequences: health, skin cancer, cataracts, weakened immunity. Environment, marine plankton death, reduced crop yields, impact on ecosystems. International action, the 1987 Montreal Protocol restricts and phases out the use of CFCs. Source, AI summary. Fluorocarbons, CFCs, also known as chlorofluorocarbons, rise to the stratosphere due to their stable chemical properties, releasing chlorine atoms under sunlight, triggering a chain reaction that destroys ozone molecules and causes holes in the ozone layer. To this end, the Montreal Protocol was signed internationally to regulate and ban the production of HCCs to protect the ozone layer from further damage. How do HCFCs destroy the ozone layer? Steady rise. HCFCs are chemically very stable substances that do not easily decompose in the lower atmosphere. Reaching the stratosphere, these gases eventually float into the stratosphere, the area where the ozone layer is located. Release of chlorine atoms. In the stratosphere, UV exposure from sunlight breaks down HCFC molecules, releasing chlorine radicals with high activity. Chain catalytic reaction. A chlorine atom can catalyze the decomposition of nearly 100,000 ozone molecules, triggering a series of ozone-depleting chemical reactions and creating holes in the ozone layer. International response. Montreal Protocol. This is an international convention signed in 1987 and officially entered into force in 1989. Prohibition of HCFC production. The protocol requires countries to phase out and ban the production of HCFCs and other ozone-depleting substances that are damaging to the ozone layer. The meaning of the ozone layer. The ozone layer absorbs most of the UV radiation from the sun, protecting the Earth's surface from excessive damage, so its integrity is crucial for the Earth's ecology. In 1985, a hole in the ozone layer was discovered. Source, ChatGPT. In 1985, scientists first observed a significant void in the ozone layer over Antarctica, ozone hole, which is one of the important evidence that human activities affect the atmosphere. Underscore 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 un. 1. Discover the process. Observation location, Antarctica, especially at the Antarctic Research Station using balloons and spectral measuring instruments. Discovery team, an observation team of scientists from the UK and other international countries. Phenomenon, every spring, September to November, ozone concentrations over Antarctica plummet, forming a huge cavity with ozone levels dropping by more than 50% from normal at its lowest. Underscore 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 un. 2. Cause. Chlorofluorocarbons, CFCs, and halons enter the stratosphere, and chlorine and bromine radicals are released after ultraviolet decomposition. Polar stratospheric clouds, PSCs formed at low temperatures in Antarctic winters, they help catalyze the destructive response of chlorine atoms to ozone. Photochemical reactions accelerate in spring sunlight, the ozone layer thins rapidly. Underscore 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 un. 3. Subsequent impact. Human health. UV rays increase skin cancer, cataracts, decreased immunity. Ecological impact. Marine plankton and land plants are harmed by UVB, affecting the food chain. Underscore 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 un. 4. International reaction. Montreal Protocol, 1987. Global limitation and phasing out of ozone-depleting substances such as CFCs, halons, etc. Scientific monitoring, continuous tracking of the recovery of the ozone layer. Data in recent years shows a slow trend of decreasing the ozone hole area. Source, AI summary. In 1985, scientists from the British Antarctic Survey officially published their findings on the Antarctic ozone layer hole in the journal Nature, pointing out that the ozone content over Antarctica decreased by about 40% in the spring, which caused global shock and attention. and promoted subsequent international environmental protection actions, such as the Montreal Protocol in 1987. Discovery process. Early observations. Satellite data actually observed the existence of holes in 1976, but the quality control algorithms at that time believed that there was an error, so the data was not adopted. Official publication. It was not until May 1985 that British scientists confirmed the serious reduction of the ozone layer over Antarctica through ground observation data and satellite data at the time, and published it to the public. The impact of ozone layer holes. Shock to the scientific community. Scientists' discoveries are much larger than previously predicted, attracting widespread attention from the scientific community. Follow-up. This discovery directly led to the signing of the Montreal Protocol in 1987 to regulate the use of environmentally harmful chlorofluorocarbons, CFCs. Causes of holes in the ozone layer. The ozone layer hole is caused by the heavy use of chlorofluorocarbons, CFCs, by humans. CFCs are decomposed by ultraviolet light in the stratosphere, releasing chlorine radicals that cause a chain reaction with ozone molecules and destroy ozone molecules. Montreal Protocol. Source: ChatGPT. The Montreal Protocol is an important international treaty for the protection of the ozone layer around the world and is known as a successful example of environmental protection. Underscore 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 un. 1. Background. In 1985, scientists discovered the Antarctic ozone hole, confirming that chlorofluorocarbons, CFCs, emitted by humans damage the ozone layer. The world recognizes that a decrease in the ozone layer increases ultraviolet rays, which are harmful to health and ecology. Underscore 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 un. 2. Signing and effect. Year of signing, 1987. Effective year, 1989. Participating countries, initially 46 countries, later almost more than 200 countries around the world joined. Underscore 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 un. 3. Main content. 1. Control of ozone depleting substances, ODs. OCFCs halons methyl bromide. 2. Phase out. O. Set timelines for reduction and phase out of various chemicals. 3. Technical and financial support. O. Developing countries receive funding and technical support to transition to alternatives. 4. Monitoring and reporting. O. Countries need to regularly monitor emissions and ozone layer conditions. Underscore 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 un. 4. Results. Emissions of CFCs and other ozone depleting substances have dropped significantly. Scientific monitoring shows a slow recovery trend of the ozone layer, and it is expected that it may return to 1980 levels by the middle of the 21st century. Becoming a successful example of international environmental treaties, showing that global cooperation can solve environmental problems that transcend borders. Source: Wikipedia. The Montreal Protocol, the full name of the Montreal Protocol on Substances that Deplete the Ozone Layer, is the United Nations Protocol on Substances that Deplete the Ozone Layer in order to prevent the continued deterioration and damage of the Earth's ozone layer by chlorofluorocarbons in industrial products, inheriting the general principles of the 1985 Vienna Convention for the Protection of the Ozone Layer. On September 16, 1987, 26 member states were invited to sign the Environmental Protection Protocol in Montreal, Canada. The protocol entered into force on January 1, 1989. 1987 edition. The Montreal Protocol stipulates strict control on the production of 5-CFC-11, CFC-12, CFC-113, CFC-114, CFC-115, and 3-C dragons, and stipulates that countries have the obligation to work together to protect the ozone layer. And so on. Countries should also hold regular conferences and report on the quantity and progress of ozone-depleting substances, and promote the research and development of alternatives and alternative technologies to replace substances such as CFCs through regulations and other means. In addition, the protocol requires countries to consider what mechanisms to use to achieve cooperation in technical assistance. The First Amendment and the London Amendment. Although the protocol stipulates that the production of CFCs will be frozen at the 1986 scale and requires developed countries to reduce manufacturing by 50% in 1988, the production of sea dragons has been banned since 1994. However, in the spring of 1988, NASA released the Global Ozone Trends Report, which pointed out that the global destruction of the ozone layer was not limited to the Antarctic and Arctic regions, and indirectly confirmed that the Montreal Protocol's control of chlorofluorocarbons was still insufficient. In view of this, the United Nations convened the second meeting of the parties to the Montreal Protocol in London, England in June 1990, and made significant amendments to the content of the protocol, the most important of which is to expand the regulated substances, in addition to the original listed items, add 10 substances such as CFC-13, carbon tetrachloride and trichloroethane, a total of 12 chemical substances, and request to accelerate the complete ban of CFCs and Sea Dragons, Annex A. Group 1, Group 2 and Annex B Group I, in 2000. Second Adjustment and Copenhagen Amendment. The Copenhagen Amendment adds 34 hydrochlorofluorocarbons to the list of controlled substances, no longer refers to HCFCs as transitional substances, requires developed and developing countries to stop the production and use of HCFCs by 2030 and 2040 respectively, and strengthens the requirement for parties to submit data on controlled substances to the Secretariat of the Conference of the Parties to the Protocol. The adjustment plan is to advance the production and consumption period of chlorofluorocarbons and Sea Dragons in developed countries by 4 years. The Third Adjustment Proposal. The Third Adjustment was adopted at the 7th Conference of the Parties held in Vienna in December 1995. The main content of the adjustment proposal is to propose a timeline for methyl bromide phase-out, allowing developing countries to delay the completion of the phase-out of substances such as CFCs and Sea Dragons by 10 years. The Fourth Amendment and the Montreal Amendment. The main content of the Montreal Amendment is to prohibit the export of various ozone-depleting substances to non-contracting parties, and to establish an import and export licensing system to supervise and restrict the import and export activities of controlled substances between contracting parties. The adjustment plan will advance the phase-out period of methyl bromide from the original 2010/2020 to 2005/2015. The Fifth Adjustment and the Beijing Amendment. The Beijing Amendment added bromochloromethane to the list of controlled substances, stipulating import and export restrictions on hydrochlorofluorocarbons. The adjustment plan adjusts the phase-out schedule for CFC substances. The Sixth Adjustment Proposal. The Sixth Adjustment Bill passed in September 2007 advanced the phase-out period of HCFCs by 10 years, stipulating that developed countries and developing countries should achieve complete phase-out of HCFCs by 2030 and 2040 respectively. Chlorofluorocarbons. Source: ChatGPT. Chlorofluorocarbons, CFCs, are a class of synthetic organic compounds composed of chlorine, Cl, fluorine, F, and carbon, C, which have been widely used in refrigeration, blowing agents, and aerosols in the past. One key features. Chemically stable, it is difficult to decompose at the ground and in the troposphere, so it can exist in the atmosphere for a long time. Non-toxic and odorless, high safety and has been widely used. Low reactivity, it does not easily react with other substances, so it does not damage the environment on the surface. Two harm to the ozone layer. 1 ascent to the stratosphere, about 15-30 km. Because of their chemical stability, CFCs can float up to high altitudes. 2 UV degrading CFCs. High altitude UV light interrupts the CFC molecule, releasing chlorine atoms, Cl. 3 chlorine atoms catalyze the destruction of ozone. A chlorine atom can cycle and destroy tens of thousands of ozone molecules. Cl plus O3 ClO plus O2 Cl and O_3 backslash right arrow ClO and O_2 Cl plus O3 ClO plus O2 Cl and OCl and O2 Cl and O backslash right arrow Cl and O_2 Cl and OCl and O2. For result. The thinning of the ozone layer. The arrival of ultraviolet, UVB, rays to the surface increases damage to humans and ecosystems. Three substitutions. HCFCs, hydrochlorofluorocarbons, less damage to ozone, but still have a certain impact. HFCs, hydrofluorocarbons, do not damage the ozone layer, but are partially greenhouse gases. Natural alternatives, such as carbon dioxide, ammonia, etc. For international control. Montreal Protocol, 1987. Global phasing out of CFCs to prevent further destruction of the ozone layer. Source: Wikipedia. Chlorofluorocarbons, CFCs, also known as CFCs, chlorofluorocarbons, CH. Due to their low activity, non-flammability and non-toxicity, chlorofluorocarbons are widely used in daily life. Freon is the trade name for several halogen carbon compounds produced by chemours, including dichlorodifluoromethane. Chlorofluorocarbons are formed by an alkane combined with fluorine and chlorine molecules through a halogenation reaction, free radical substitution reaction, and the hydrogen atom of the alkane is replaced by a fluorine or chlorine atom. Hydrogen atoms that have not been replaced are called hydrochlorofluorocarbons, HCFCs. Some of the used chlorofluorocarbons rise to the stratosphere, bottom of the stratosphere. Due to their low activity, low biodegradability, and insolubility in water, chlorofluorocarbons are difficult to decompose. Chlorofluorocarbons decompose chlorine radicals when exposed to ultraviolet rays from the sun, damaging the ozone layer. Since this destruction is a chain reaction, the power is quite staggering. It is estimated that a single chlorine atom can wipe out nearly 100,000 ozone molecules in a few months. Greenhouse effect. Source: ChatGPT. The greenhouse effect is a natural process by which the Earth's atmosphere absorbs and re-radiates heat energy, keeping the Earth's surface at a temperature suitable for life. It is like a layer of greenhouse glass, allowing heat to enter but not easily out. One principle. 1. Solar radiation enters the Earth. Sunlight penetrates the atmosphere in the form of shortwave radiation and hits the surface. 2. Surface absorption and re-radiation. After the surface absorbs solar energy, it is converted into infrared long-wave radiation. 3. Atmospheric absorption and re-radiation. Greenhouse gases, e.g., CO, CH, NO, O, water vapor, absorb long-wave radiation and re-radiate heat to the surface, keep the surface warm. Two major greenhouse gases. Gas source note. Carbon dioxide, CO. Burning fossil fuels, deforestation. The most important anthropogenic greenhouse gas. Methane, ch animal husbandry, biogas, landfill. The endothermic capacity is about 28-36 times that of CO. Nitrous oxide, NO. Agricultural fertilizer, burning. The endothermic capacity is about 265 times that of CO. Chlorofluorocarbons, CFCs, refrigerants, aerosols. It has a strong heat absorption ability and also destroys the ozone layer. Water vapor, HO. Evaporates naturally. The most important natural greenhouse gas. Three. Influence. Positive, natural greenhouse effect. Maintain an average temperature of about 15 degrees Celsius on Earth, which is suitable for living organisms. Negative, global warming. Human activities increase CO, CH, etc. Excessive greenhouse effect. Rising temperatures, melting glaciers, rising sea levels, and abnormal climatic conditions. For human response. Reduce fossil fuel use and develop renewable energy. Protect forests and increase carbon absorption. International cooperation to reduce emissions, such as the Paris Agreement. Source: Wikipedia. The greenhouse effect is the effect of a planet's atmosphere absorbing radiation energy, causing the planet's surface to heat up. Due to the greenhouse effect, the surface temperature of the planet will be higher than it would be without an atmosphere. In the past, it was thought that the mechanism was similar to the mechanism by which greenhouses raise the temperature in the middle, so it was called the greenhouse effect. Many studies have pointed out that human factors have exacerbated the greenhouse effect on the Earth, causing the effect of global warming. Solar radiation is mainly due to shortwave radiation, while terrestrial radiation and atmospheric radiation are long-wave radiation. The atmosphere absorbs long-wave radiation strongly and short-wave radiation weakly. When sunlight shines on the Earth, part of the energy is absorbed by the atmosphere, part of it is reflected back into the universe. About 47% of the energy is absorbed by the Earth's surface, and the Earth's surface emits absorbed energy into the universe in the form of infrared rays day and night, and some of it is absorbed by the atmosphere. The atmosphere is like a glass-covered greenhouse, which stores a certain amount of heat, so that the Earth does not rise sharply when illuminated by the sun like the moon without an atmosphere, and the temperature drops sharply when not illuminated by the sun. Some theories suggest that the increase in greenhouse gases increases the amount of heat retained by the Earth as a whole, leading to global warming. Without the greenhouse effect, the Earth would be too cold for human habitation. It is estimated that without the atmosphere, the average temperature of the Earth's surface would be 18 degrees C. It is the greenhouse effect that keeps the average temperature of the Earth at 15 degrees Celsius, but too many greenhouse gases cause the average temperature of the Earth to be higher than 15 degrees Celsius. At present, human activities have increased the content of greenhouse gases in the atmosphere, and due to the burning of fossil fuels and water vapor, carbon dioxide, methane, etc., the emission of gases is absorbed and retained by infrared radiation, resulting in an increase in global surface temperature, exacerbating the greenhouse effect and causing global warming. To address this issue, the United Nations has established the Framework Convention on Climate Change to control greenhouse gas emissions and prevent the Earth's temperature from rising, affecting the ecology and environment. The Earth absorbs electromagnetic radiation emitted by the Sun, such as ultraviolet light, visible light, and near-infrared rays. Of all the radiant energy that can be received in the upper part of the atmosphere and clouds reflect 26% of the energy into space, while the atmosphere and clouds themselves absorb 19% of the energy. Most of the remaining energy is absorbed by the Earth's surface, because the temperature of the surface is much colder than that of the Sun, so the wavelengths of far infrared rays emitted by the Sun are much longer than those emitted by the Sunday. In addition to absorbing electromagnetic waves emitted by the Sun and thermal radiation from the Earth, the atmosphere also receives energy from the sensible heat and latent heat flux of the ground. The atmosphere radiates energy above and below, and some of the energy radiated downwards is absorbed by the Earth's surface, so the surface temperature will be higher than the surface temperature without the atmosphere. Differences in the spectrum of solar radiation above the atmosphere and at sea level. An ideal thermally conductive black body would receive heat from solar radiation at a temperature of about 5.3 degrees Celsius if it were located on Earth. However, because the Earth reflects about 30% of the solar radiation energy, its ideal effective temperature, the temperature at which the radiated heat of the black body is the same as the heat absorbed by the black body, should be 18 degrees C. The surface temperature of the hypothetical planet described above, 18 degrees C, is about 33 degrees Celsius lower than the average surface temperature of 14 degrees Celsius on Earth. The underlying mechanism described above can be quantified in many ways, and none of these can affect the underlying mechanism. The atmosphere near the ground does not absorb thermal radiation, except in the wavelength bands corresponding to the greenhouse effect, and most of the heat loss from the surface is due to the propagation of sensible and latent heat. The higher the altitude in the atmosphere, the greater the heat loss from its radiation because the concentration of water vapor, an important greenhouse gas, decreases. The greenhouse effect can be thought of as adding a surface to the middle troposphere, and the properties of the surface are adjusted according to the rate of vertical decline in air temperature. This simple model assumes that the temperature is in steady state, but the actual temperature will change due to changes in the day-night cycle, seasonal cycle, and climate. At night, because of the low emissivity of the atmosphere, the atmospheric temperature will be lower, but it will not change much. Diurnal temperature changes decrease with altitude. In areas with significant radiation effects, they are closer to the ideal greenhouse effect described above. The temperature of the Earth's surface is about 255 K, and it emits long waves of infrared rays at wavelengths of about 400 μm. Greenhouse gases are transparent to incoming solar radiation, do not absorb and do not reflect, but absorb energy at this wavelength. Each layer of the atmosphere with greenhouse gases absorbs some of the energy emitted from below, and then emits it up and down, achieving a balance between emitted energy and absorbed energy. Therefore, the lower the atmosphere, the warmer it is. Increasing the concentration of greenhouse gases also increases the energy absorbed and re-emitted, which warms the atmosphere and eventually the ground. Greenhouse gases including most diatomic gases made up of two different atoms, e.g. carbon monoxide, and all gases made up of three or more atoms can absorb and emit infrared radiation. Although 99% of the dry atmosphere, oxygen, nitrogen, and argon, does not absorb and emit infrared light, molecular collisions allow the energy absorbed and emitted by greenhouse gases to be transferred to other non-greenhouse gases. Hydrofluorolefins. Source: ChatGPT. Hydrofluorolefins, HFOs, are a new class of fluoroolefins that are mainly used as substitutes for refrigerants and aerosols, characterized by their very low destruction to the ozone layer and much lower greenhouse effect potential, GWP, than traditional HFCs. Underscore 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 un. 1. Basic characteristics. Chemical composition, contains hydrogen, H, fluorine, F, carbon, C, usually with double bonds, olefin properties. Physical properties, gas or liquid refrigerant, compressible and liquefiable. Environmental characteristics. Ozone depletion potential, ODP, 0 does not damage the ozone layer. The global warming potential, GWP, is low and has a low impact on the climate. Underscore 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 un. 2. Application. Refrigerants, air conditioners, refrigerators, freezers, etc. aerosols, cosmetics, cleaning supplies, pharmaceutical sprays, etc. Substitute role, replaces CFCs, HCFCs and some HFCs, reducing impact on the ozone layer and climate. Underscore 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 un. 3. Comparison with traditional refrigerants. Gas type ozone depletion potential, ODP, global warming potential, GWP, note. CFC's high prohibited use. HCFC's middle is being phased out. HFC's zero high it does not destroy ozone, but contributes to warming. HFO's zero low new environmentally friendly refrigerant. Source, Wikipedia. Hydrofluorolefins, HFO, are unsaturated organic compounds composed of hydrogen, fluorine, and carbon. These organofluorochemicals are often used as refrigerants, unlike traditional chlorofluorocarbons, CFCs, and hydrofluorocarbons, HFCs, both of which are saturated organic compounds, and hydrofluorolefins are olefins. HFO refrigerants are zero ozone depletion potential, OZP, and low global warming potential, GWP, refrigerants, which are more earth-friendly and good alternatives than chlorofluorocarbons, hydrofluorocarbons, and hydrochlorofluorocarbons. HFO refrigerants belong to the fourth generation of refrigerants, with a global warming potential of only 0.1% of hydrofluorocarbons. The HFOs currently in use are 2,3,3,3-tetrafluoropropylene, HFO-1234YF, and 1,3,3,3-tetrafluoropropylene, HFO-1234ZE. 1-chloro-3,3,3-trifluoropropylene, HFO-1233ZD, is also under development. Trifluoroacetic acid. Source, ChatGPT. Trifluoroacetic acid, TFA, is a fluorinated organic acid with the chemical formula CFCOOH. It is of some interest in environmental science and industrial applications, especially in relation to hydrofluorolefins, HFOs, or products after the decomposition of fluorinated gases. Underscore 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 un. 1. Basic nature. Chemical formula CFCOOH. Properties: strongly acidic, colorless liquid, soluble in water and most organic solvents. Stability: fluorine atoms make molecules very stable and difficult to degrade quickly in the environment. Underscore 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 un. 2. Source. 1. Industrial source. O. It is used in organic synthesis, analytical chemical reagents, pharmaceuticals and materials industries. 2. Atmospheric chemical sources. O. Certain fluorinated gases, e.g., HFCs, HFOs, may form trifluoroacetic acid after decomposition in the atmosphere. Underscore 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 un. 3. Environmental impact. Water volume accumulation. Due to its chemical stability, TFA accumulates in rainwater and may be absorbed by plants and aquatic organisms. Ecotoxicity. Current studies have shown limited biotoxicity at low concentrations, but long-term accumulation still requires concern. Climate and ozone. TFA itself does not destroy the ozone layer and is not a greenhouse gas, but it is a byproduct of the degradation of certain new refrigerants. Underscore 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 un. 4. Importance. In the alternative refrigerant, HFOs, environmental assessment, trifluoroacetic acid is considered a possible environmental pollutant and its concentration and impact need to be monitored. Source, Wikipedia. Trifluoroacetic acid, chemical formula, CF3COOH, abbreviated as TFA, is a perfluorinated derivative of acetic acid and the simplest perfluorocarboxylic acid compound. Colorless volatile fumesizing liquid, similar to acetic acid odor, hygroscopic and pungent odor. It is miscible with water, fluorohydrocarbons, methanol, ethanol, ether, acetone, benzene, carbon tetrachloride, and hexane, and can partially dissolve carbon disulfide and alkanes above 6 carbons, making it an excellent solvent for proteins and polyesters. It is strongly acidic due to the influence of electron-absorbing trifluoromethyl groups. It is 100,000 times more acidic than acetic acid. It can be reduced by sodium borohydride or lithium aluminum hydride to trifluoroacetaldehyde and trifluoroethanol. Stable above 205 degrees Celsius, esters and amide derivatives are easily hydrolyzed, so sugars, amino acids and peptide derivatives can be prepared in the form of acids or anhydrides. It is easy to dehydrate into trifluoroacetic anhydride under the action of phosphorus pentoxide. It decomposes into fluoroform and carbon dioxide in the presence of aniline. Ammonia. Source: ChatGPT. Ammonia, NH, is an inorganic compound composed of nitrogen and hydrogen, often found in gas form and has a pungent odor. It plays an important role in industry, biology, and the environment. One basic nature. Chemical formula, NH. Physical properties: colorless gas, density less than air, easily soluble in water to form ammonium hydroxide, NHO. Smell: pungent smell, can be smelled at low concentrations. Flammability: 15-28% concentration in air is in the flammability range. Two source. 1 natural source. Soil and water microorganisms break down organic matter, proteins, urea, to produce ammonia. Volcanic gases, animal waste. 2 industrial source. Chemical fertilizers, synthetic nitrogen fertilizers, refrigerants, chemical raw materials, detergents, etc. Three application. Fertilizer, nitrogen source, is an important fertilizer in agriculture. Industry, synthetic urea, nitric acid, explosives, refrigerants, such as ammonia refrigeration systems. Environmental treatment, neutralize acidic wastewater, partial air pollution control. For health and environmental impact. Low concentration, irritation of eyes, nose, and respiratory tract, watery eyes, coughing. High concentration, it can cause dyspnea, pulmonary edema, and even death. Environmental impact, large ammonia emitting can form nitrogen oxides, acid rain, eutrophication, algae overgrowth. Source: Wikipedia. Ammonia, English, ammonia, or ammonia, anhydrous ammonia, once transliterated as argon, ammonia, molecular formula NH3, is a colorless gas with a strong pungent odor, urine smell, and is easily soluble in water. At room temperature and pressure, 1 unit volume of water can dissolve 700 times the volume of ammonia. Ammonia is important for life on Earth and is an important component of all foods and fertilizers. Ammonia is also a direct or indirect component of many pharmaceuticals and commercial cleaning products, and is corrosive and dangerous. Due to its wide range of uses, ammonia is one of the most produced inorganic compounds in the world, with about 80% used to make fertilizers. In 2006, global production of ammonia was estimated at 1.465 million tons, mainly used to manufacture commercial cleaning products. Ammonia can provide lone electron pairs, so it is also a Lewis base. UV amplification. Source: ChatGPT. Ultraviolet amplification, UV amplification, refers to the increase in UV intensity due to the thinning of the ozone layer, with more ultraviolet rays, especially UVB, penetrating the atmosphere and reaching the Earth's surface. One formation causes. 1. The ozone layer is thinned. Chemicals such as chlorofluorocarbons, CFCs, and halons release chlorine and bromine atoms after entering the stratosphere, catalyzing the destruction of ozone molecules. Stratospheric ozone decreases, UV absorption decreases. 2. UV enhancement. UVB, 28320 nm, increased surface intensity of UV irradiation. The ozone hole over Antarctica gives the highest UV intensity in spring, which can increase several times compared to normal years. To impact human health. Skin, sunburn, accelerated skin aging, increased risk of skin cancer. Eyes, cataracts, corneal damage. Immune system suppression. Ecosystem. Marine plankton deaths affect the food chain. Crop photosynthesis is inhibited, harvest declines. Forests and terrestrial ecosystems may also be damaged. Climate and atmospheric chemistry. Increases the rate of atmospheric chemical reactions, such as ground-level ozone formation. Underscore 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 un. 3. Mitigation measures. Restriction of ozone-depleting substances, CFCs, HCFCs, Montreal Protocol. Use alternative refrigerants, HFCs, HFOs, and control emissions. Raise public awareness of sun protection and avoid exposure during high UV hours. The reason for the increase in the hole in the ozone layer. Source: ChatGPT. The main reason for the increase in the ozone hole, particularly the Antarctic ozone hole, is a combination of anthropogenic activity and specific atmospheric conditions. Underscore 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 un. 1. Human factors. 1. Chlorofluorocarbons, CFCs. In the past, it was widely used in refrigerants, aerosols, foams, etc. High stability rise to stratosphere UV decomposition release chlorine atoms. Chlorine atoms can cycle and destroy tens of thousands of ozone molecules. 2. Halons. Used in fire extinguishers, it releases bromine atoms, has a stronger ozone damaging capacity than chlorine. 3. Other ozone depleting substances, ODs. For example, methyl bromide, HCFCs, etc. Underscore 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 un. 2. Natural factors. 1. Polar low temperatures. Antarctic winter temperatures can drop below 78 degrees C, forming polar stratospheric clouds, PSCs. PSC provides a chemical reaction surface that accelerates chlorine and bromine catalyze ozone destruction. 2. Spring light. Antarctic spring sunlight returns UV light, triggers rapid photochemical reactions, ozone decreases rapidly. 3. Airflow mode. The closed air mass of the polar stratosphere restricts gas exchange, concentrating the destruction reaction and forming a significant cavity. Underscore 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 un. 3. Causes of enlargement. Historical emissions accumulation. CFCs emitted large amounts in the 20th century, with chlorine atoms accumulating in the atmosphere. Polar winter low temperatures continue, PSC formation is frequent, and reactions intensify. Increased sunlight in spring, the rate of destruction increases instantly, the cavity area expands. Source: AI summary. The main cause of the increase in the ozone layer hole is the release of chlorofluorocarbons, CFCs, by humans, which will decompose chlorine atoms when released into the stratosphere, thereby catalyzing the decomposition of ozone molecules and continuing to deplete ozone. In addition, recent studies have found that extreme weather events such as wildfires and volcanic eruptions in Australia release tiny particles, triggering new chemical reactions and accelerating the destruction of the ozone layer. At the same time, global warming has led to a cooling of the stratosphere, which may also slow the recovery of the ozone layer. Detailed explanation of the reasons. Effects of CFCs. CFCs are refrigerants or blowing agents in products such as refrigerators, air conditioners, sprays, etc. They are ground stable and can float to the stratosphere before being decomposed by ultraviolet light, releasing destructive chlorine atoms. A chlorine atom can continuously react with ozone molecules, depleting a large amount of ozone molecules and causing the ozone layer to decrease. Exacerbation of extreme weather events. Wildfires and volcanic eruptions. Large-scale wildfires, such as Australia's Black Summer in 2020, and submarine volcanic eruptions can carry large amounts of soot, tiny particles, and acidic materials into the stratosphere. Chemical reactions. These particles can trigger new chemical reactions, such as acidic substances and soot that can react with CFC's decomposition products, forming substances that further destroy ozone, exacerbating the expansion of ozone holes. Indirect impacts of climate change. The increase in greenhouse gases such as carbon dioxide leads to a decrease in stratospheric temperatures, which increases the formation of polar vortices and prolongs their stability, creating more favorable conditions for CFCs to destroy ozone. Therefore, even if CFCs emissions have been limited, the effects of climate change may still slow the recovery of the ozone layer. Current status. Although the Global Montreal Protocol has effectively reduced the production of CFCs, it takes a long time for the ozone layer to recover due to the long lifespan of CFCs in the air. Recent studies have shown that the recent expansion of the ozone hole may not only be caused by CFCs, but also closely related to climate change, atmospheric dynamics, and extreme weather events. Ozone layer repair. Source: ChatGPT. Ozone layer restoration refers to the process of gradually recovering ozone concentration and restoring a healthy thickness to the ozone layer after international cooperation and reducing ozone depleting substance, ODs, emissions. Underscore 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 un. 1. Background. Source of the problem: chlorofluorocarbons, CFCs, halons, and other ozone-depleting substances destroy stratospheric ozone. International action. In 1987, the Montreal Protocol was signed, which globally restricted the production and use of ODs such as CFCs. Underscore 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 un. 2. Repair mechanism. 1. Reduce ODs emissions. With the reduction of production of CFCs, HCFCs, and halons, the concentration of active chlorine and bromine in the stratosphere decreases. 2. Natural photochemical reactions. Ozone is gradually regenerated in the stratosphere. O2 UV2O, O plus O2O30 underscore 2 backslash ec right arrow UV2O backslash quad O and O underscore 2 backslash right arrow O underscore 3 O2 UV2O, O plus O2O3. Reactive chlorine concentrations decrease, catalytic destruction reactions weaken, ozone buildup picks up. 3. Long-term cumulative effect. Because ODs have a long lifespan in the atmosphere, CFCs can reach 50-100 years, ozone layer repair is a slow process. Underscore 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 un. 3. Observation and prediction. Antarctic cavity. Recent observations have shown that the area of the cavity is shrinking year by year. Global trends. Scientific models predict that the ozone layer is expected to return to pre-1980 levels by the mid-21st century if global compliance with the Montreal Protocol continues. Underscore 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 un. 4. Successful experiences. The Montreal Protocol is a model of global environmental cooperation. Combining scientific findings, international policies, technological alternatives, successful emissions reductions. Shows that human action can reverse global environmental problems. Source: BBC News. In the late 70s, Jonathan Shanklin, a meteorologist at the British Antarctic Survey, spent a lot of time in an office in Cambridge, studying pending data from the southernmost continent of the Earth. These data are calculated values and written data from the Dobson spectrophotometer, a ground-based instrument that measures changes in atmospheric ozone, and Shanklin's job is to oversee the digitization of this data. As time passed, Shanklin began to notice that something was happening. After nearly 20 years of fairly stable measurements, he noticed that ozone levels began to decline in the late 70s of the 20th century. At first, Shanklin's boss doesn't trust his analysis, which frustrates him. By 1984, the thickness of the ozone layer over the Hawley Bay Research Station in Antarctica had decreased by a third compared to previous decades. Shanklin and his colleagues Joe Farman and Brian Gardner published their findings the following year, arguing that it was related to a man-made compound known as chlorofluorocarbons, CFCs, also known as chlorofluorocarbons, which are used in aerosols and cooling equipment. Their discovery, the thinning of the ozone layer over Antarctica, is known as the ozone layer hole. This discovery shocked the world. Predictions of detrimental effects on human health and ecosystems that ozone layer depletion have sparked fear among the public. This has also led to more scientific research and inspired governments around the world to collaborate like never before. Ozone is mainly found in the atmospheric stratosphere 10 to 50 kilometers above the Earth's surface. The ozone layer forms a protective layer on Earth, absorbing damaging UV radiation from the sun. Without it, there could be no life on Earth. In the 50s of the 20th century, the British Antarctic Survey began measuring ozone concentrations over Antarctica for the first time. But decades later, the problem became clear. In 1974, scientists Mario Molina and F. Sherwood Rowland published a paper theoretically stating that chlorofluorocarbons may destroy ozone in the Earth's stratosphere. Until then, it was believed that CFCs were harmless, but Molina and Rowland believed this was wrong. It was found to have been attacked by the industry, who insisted that CFC products were safe. The study has also been questioned by scientists. Some scientists believe that ozone loss is slight, between 2 to 4%. And many people think it will take centuries to happen. By the 70s of the 20th century, CFCs were ubiquitous around the world, used as coolants in refrigerators and air conditioners, aerosol spray cans and industrial cleaning agents. Just 10 years later, in 1985, the British Antarctic Survey confirmed a hole in the ozone layer and thought it was related to chlorofluorocarbons, which proved Molina and Rowland's findings correct, and the two eventually won the 1995 Nobel Prize in Chemistry. To make matters worse, the ozone hole is expanding much faster than expected. It's shocking, said Shanklin, an honorary retired researcher at the British Antarctic Survey. Since then, scientists have been studying why this phenomenon occurs. In 1986, as the Antarctic winter drew to a close, Susan Solomon, a researcher at the National Oceanic and Atmospheric Administration, led a team of scientists to McMurdo Base to find answers. At that time, scientists were discussing three possibilities, one of which was proposed by Solomon. The answer may lie in chemistry, which includes chlorine in polar stratospheric clouds, which occur at high latitudes and only form at low temperatures in polar winters. It's a huge mystery, said Solomon, who is now a professor of atmospheric chemistry and climate science at the Massachusetts Institute of Technology, MIT. Her research explains why the ozone hole in Antarctica appears. All the data suggest that the increase in chlorine caused by human use of chlorofluorocarbons in polar stratospheric clouds are the triggers for this problem. Satellite monitoring confirmed that ozone loss expanded over a wider area, about 770 square miles, 20 million square kilometers. Ozone destruction poses a serious threat to the planet, rising rates of skin cancer and cataracts in humans, harming plant growth, crops, and animals, and also affecting reproductive problems for fish, crabs, frogs, and phytoplankton, the basis of the marine food chain. International cooperation in prevention and control is imperative. The ozone hole is such a serious threat, why do we no longer hear about it often? Laura Revell, an associate professor of environmental physics at the University of Canterbury in New Zealand, said, "This is no longer the kind of concern that used to be. This is mainly due to unprecedented collaborative measures taken by governments to address this issue." International organizations initially believed that ozone depletion was small and would last for a long time, so they took a cautious approach to protecting the ozone layer. In 1977, a global action plan was implemented, requiring the monitoring of ozone and solar radiation, the study of the effects of ozone depletion on human health, ecosystems, and climate, and the cost-effectiveness assessment of control measures. Just a few months before British scientists discovered the ozone layer hole, the 1985 Vienna Convention, called for further research. But it did not enact legally binding controls to reduce CFCs, which disappointed many. After the discovery of the ozone hole, increased investment in scientific research, the allocation of economic resources, and coordinated international political action turned the tide. The Montreal Protocol, adopted in 1987, protects the ozone layer by phasing out ozone-depleting chemicals. To encourage compliance, the treaty recognizes common but differentiated responsibilities, establishes timelines for phased emission reductions for developed and developing countries, and establishes a multilateral fund to provide financial and technical assistance to developing countries in meeting their obligations. In the 90s of the 20th century and the beginning of the 21st century, the production and consumption of chlorofluorocarbons stopped. By 2009, 98% of the chemicals restricted by the treaty had been phased out. But when scientific evidence suggests further action is needed, the treaty allows for the implementation of 6 amendments, such as the use of alternatives such as hydrofluorochlorofluorocarbons, HCFCs, and hydrofluorocarbons, HFCs, which, while good for the ozone layer, are harmful to the climate. For example, the most commonly used HFCs have almost 2,000 times the global warming potential of carbon dioxide. The climate benefits of the treaty have side effects. In 2010, the Montreal Protocol reduced emissions by 9.7 to 125 billion tons of carbon dioxide equivalent, about 5 to 6 times the target of the Kyoto Protocol, an international treaty to reduce greenhouse gas emissions in 1997. The Kigali Amendment, passed in 2016, would limit the use of HFCs, which would help avoid global warming by 0.5 degrees Celsius by 2100. Revell said, "You could say that the Montreal Protocol has been much more successful than any other climate agreement we have signed so far. Since the adoption of the Montreal Protocol, every country on the planet has signed it, the only treaty that has been the most universally ratified to date. This is widely regarded as a victory for international environmental cooperation." According to some models, the Montreal Protocol and its amendments have helped prevent up to 200 skin cancers a year and have avoided millions of cataract cases worldwide. If the world had not banned the use of chlorofluorocarbons, the ozone layer we would find today would have been depleted on a large scale. Solomon said, "By 2050, we are already certain that there will be an ozone hole throughout the planet and the Earth will become uninhabitable." Solomon believes 3 factors contribute to a quick solution: the danger of the ozone hole, reality getting everyone to act, and intuitive satellite imagery making the problem easy to understand, and feasible solutions, making it faster and easier to find alternatives to ozone-depleting substances. Today, the ozone hole still exists, forming over Antarctica every spring. In summer, when stratospheric air from lower latitudes mixes in, it closes again until the cycle begins again the following spring. But there is evidence that it is recovering more or less, Solomon said. According to scientific assessments, the ozone layer is expected to return to pre-1980 levels around the middle of this century. Due to the long molecular life of ozone-depleting substances, the repair process is slow. Some remain in the atmosphere for 50 to 150 years before decaying. Despite the overall success of the Montreal Protocol, there were some setbacks. For example, in 2018, the concentration of monofluorotrichloromethane, CFC-11, which has been banned since 2010, did not decline as quickly as expected, indicating undeclared emissions somewhere. The U.S. Environmental Investigation Agency tracked these gases from factories in China that are producing insulating foam. The news was made public, and the Chinese government quickly took action, and scientists say that we are now back on track. Shanklin believes that this highlights the importance of long-term monitoring of environmental variables, whether chlorofluorocarbons, temperature, or biodiversity indicators. If we don't monitor the environment, we don't know if we're in trouble, and if you don't know you're in trouble, you can't take precautions, and I think that's a key part of the story. The future is not without risks. Volcanic eruptions usually cause short-term ozone loss, and nitrous oxide, a potent greenhouse gas emitted from agricultural fertilizer applications, is also a potent ozone-depleting substance. However, it is not controlled by the Montreal Protocol, Revel explained, and emissions are growing. There are also the effects of activities that we don't fully understand, but they can bring risks, such as rocket launches. There is also the idea of using geoengineering, to avoid global warming, by injecting aerosols into the stratosphere. These aerosol particles reflect sunlight back and thus cool the planet. Revel said, "It's really important that we keep in mind the lessons learned from the ozone hole story and make sure we're constantly aware of what's going on in the stratosphere. The risk is that if we don't make this assessment in advance, we will cause some unforeseen damage to the ozone layer." People tend to compare the ozone layer hole to climate change. However, while the Montreal Protocol does prove that we can solve major environmental problems, the comparison ends there. CFCs happen to be replaceable, but fossil fuels that make greenhouse gases are ubiquitous in our way of life and almost impossible to easily replace, and so far most governments and businesses have refused to reduce fossil fuel emissions. For Shanklin, it's sad that we're stagnant on climate action and still debating what we might do, because we have such a clear example to learn from. Shanklin said, "The creation of the ozone hole shows how quickly we can change our planet's environment to avoid making it worse, and politicians are not taking this lesson seriously. To be fair, climate warming is a bigger problem. Politicians have a greater responsibility for this." Chlorine radicals. Source: ChatGPT. Chlorine radicals, Cl, are highly reactive chlorine atoms that play a key role in stratospheric ozone depletion. One source. Chlorofluorocarbons, CFCs, decompose. OCFCs are highly stable and can rise to the stratosphere. O decomposition and release of chlorine atoms under ultraviolet irradiation. CFCl3 UVCFCl2 plus ClCFCl_3 / Ecritero UVCFCl_2 plus ClCFCl3 UVCFCl2 plus Cl. Halons decompose. O releasing bromine atoms. Bromine also produces free radicals, but is more efficient at destroying ozone than chlorine. Two ozone depletion mechanism. Chlorine radicals catalyze ozone decomposition in the stratosphere, forming cyclic reactions. 1. Chlorine reacts with ozone. Cl plus O3 ClO plus O2 Cl plus O_3 / right arrow ClO plus O_2 Cl plus O3 ClO plus O2. 2. ClO reacts with oxygen atoms. ClO and OCl and O2 ClO plus O / right arrow Cl plus O_2 ClO plus OCl and O2. Feature: 1 chlorine radical can cycle and destroy tens of thousands of ozone molecules, so it is very efficient. Three. Influence. Ozone layer thinning. UV rays enhance health risks such as skin cancer, cataracts, and immunosuppression. Ecosystems, marine plankton and plants are damaged by UV rays. Source: AI summary. Chlorine radicals, Cl, are chemicals that are highly active due to their unpaired electrons and are produced during light exposure or certain chemical reactions such as bleach breakdown. Due to their powerful oxidizing activity, chlorine radicals are able to react with many substances and are commonly used to purify water, bleach clothes, and disinfect. What are chlorine radicals? Unstable and highly active, chlorine radicals, often expressed as Cl, refer to a chlorine atom that has an unpaired electron. This instability makes it very active, actively grabbing electrons from other molecules to achieve a steady state. Highly oxidizing, because it robs electrons. Chlorine radicals are strong oxidants that can react with many organic matter and micropollutants to convert them into other substances. Sources of chlorine radicals. Light exposure. In natural water bodies or industrial water treatment systems, light exposure can prompt chlorine atoms to produce chlorine radicals. Decomposition of bleach. Household bleach, such as sodium hypochlorite, can produce chlorine radicals when they break down. Uses and effects of chlorine radicals. Water treatment. Chlorine radicals are used in water treatment systems to break down and convert microcontaminants in water due to their high activity. Bleaching and disinfection. Chlorine radicals are one of the main active ingredients in chlorine-based bleaches, such as household bleach, which have the effect of bleaching clothes and disinfecting and sterilizing. Chemical reactions. Chlorine radicals are also key intermediates in radical substitution reactions, such as the reaction of alkanes with chlorine. Dangers to be aware of. Risk of mixing with other chemicals. Bleach, a source of chlorine radicals, should not be mixed with hydrochloric acid, as this can produce highly toxic chlorine gas and can trigger an explosion. Avoid contact with ammonia-containing substances. In domestic settings, avoid using bleach to clean urine stains, as ammonia in urine can react with chlorine radicals to form toxic chloramine. Chlorine-oxygen radicals. Source: ChatGPT. Chlorine monoxide radicals, ClO, are important intermediate products in the stratospheric ozone depletion cycle, produced by chlorine radicals reacting with ozone or oxygen atoms. One source. Produced by the reaction of chlorine radicals, Cl, with ozone, O. Cl plus O3 ClO plus O2 Cl plus O underscore 3 backslash right arrow ClO plus O underscore 2 Cl plus O3 ClO plus O2. Chlorine oxygen radicals are highly reactive free radicals that can participate in the subsequent catalytic decomposition of ozone. Two ozone destruction cycle. 1 Cl reaction with O to form ClO. Cl plus O3 ClO plus O2 Cl plus O underscore 3 backslash right arrow ClO plus O underscore 2 Cl plus O3 ClO plus O2. 2 ClO reacts with oxygen atoms to form Cl. ClO and OCl and O2 ClO plus O backslash right arrow Cl plus O underscore 2 ClO plus OCl and O2. Cyclic characteristics. O-chlorine oxygen radicals are just intermediate products, but they can circulate continuously, allowing a single chlorine atom to destroy tens of thousands of ozone molecules. Three environmental impact. Ozone layer thinning. UVB boosts skin cancer, cataracts, decreased immunity. Antarctic ozone hole formation is closely related to ClO reactions in the polar stratosphere. Source: AI summary. Chloride oxygen radicals are chemical terms that refer to free radicals that contain chlorine and oxygen atoms and are strongly oxidizing. These free radicals can act as oxidants in chemical reactions and can react with many substances, such as chlorine radicals in bleaching, which can break down stains or dyes. What are free radicals? Free radicals are chemically unstable molecules with unpaired electrons. Due to their instability, free radicals actively seek to bind to other molecules to achieve stability, which makes them highly reactive. Characteristics and applications of chlorine-oxygen radicals. Strong oxidants. Chlorine radicals are strong oxidants capable of oxidizing and damaging the structure of other substances. Bleaching and disinfection. Chlorine radicals are produced in bleaching agents such as sodium hypochlorite, which can effectively bleach clothes and eliminate stains, and are also disinfectants. Industrial uses. In industry, chlorine-containing compounds such as chlorine dioxide can be used to bleach wood pulp, oils, textiles, etc. Notes. Hazards of mixing with other chemicals. Chlorine bleach should never be mixed with acids, such as hydrochloric acid, or certain cleaning agents, such as ammonia-containing cleaners, as this can produce toxic chlorine or toxic chloramine, which can even cause explosions. Effects on the human body. While beneficial in dealing with stains in bleach, excess free radicals can cause damage to human cells and may accelerate aging. Oxygen molecule. Source: ChatGPT. The oxygen molecule, O, a diatomic molecule made up of two oxygen atoms, is one of the most important gases in the Earth's atmosphere. One basic nature. Chemical formula, O. Physical properties: colorless, odorless gas. Content: approximately 21% of dry air. Activity: relatively stable at room temperature, but easily involved in chemical reactions under high temperature or catalytic conditions. Two function and function. 1. Respiratory effect. Organisms such as the human body, animals, and microorganisms use oxygen molecules for aerobic respiration and release energy. C6H12O6 plus 6026 CO2 plus 6H2O and energy C_6H_12O_6 plus 60_2 right arrow 6CO_2 plus 6H2O plus energy C6H12O6 plus 6026 CO2 plus 6H2O and energy. 2. Ozone, O, is produced. O. Stratospheric ultraviolet light breaks down oxygen molecules into monooxygen atoms, O. O2 UV2O_2 ec right arrow UV2O2 UV2O. O. Single oxygen atoms combine with oxygen molecules to form ozone. O plus O2O3 O plus O_2 right arrow O_3 O plus O2O3. O. Therefore, oxygen molecules are the basic substances for the formation of the ozone layer. 3. Combustion and chemical reactions. O. It participates in combustion and oxidation reactions, supporting flame and industrial oxidation processes. Three. Environmental and ecological significance. Life essential, all aerobic organisms depend on O breathing. Atmospheric balance, maintain the Earth's climate and oxygen cycle. Ozone layer, oxygen molecules are the raw materials for stratospheric ozone generation and repair. Source, AI summary. The oxygen molecule is the most common elemental form of the element oxygen and has the chemical formula O2. It is formed by two oxygen atoms bonded together by covalent bonds and is the basic particle that makes up oxygen. Under normal conditions, it is a colorless and odorless gas that is one of the main components of the Earth's atmosphere and is essential for the survival of animals and plants. Composition and structure. Diatomic molecule, each oxygen molecule, O2, is made up of two oxygen atoms. Covalent bonds. Covalent bonds are formed between two oxygen atoms to bind. Paramagnetism. Oxygen molecules are a kind of odd electron molecule, so they are paramagnetic, and liquid oxygen is pale blue and can be attracted to magnets. Properties and functions. Gaseous state. Under standard conditions, oxygen molecules exist in the form of gases. Oxidizer. In redox reactions, it participates in various chemical reactions as a strong oxidant, including combustion, respiration, and more. Essential for survival. For animals and plants on Earth, oxygen molecules are essential for survival. Form of existence. Air. Oxygen molecules are one of the main components of air, accounting for about 21% of the volume of air. Water. Oxygen makes up about 88% of the water mass. Other forms. Oxygen also exists in other forms, such as ozone, O3, which is made up of 3 oxygen atoms, and other compounds formed by combining with other elements. Conclusion. The ozone layer is a vital protective barrier for the planet, protecting us from harmful UV rays and maintaining ecosystem and climate balance. However, ozone-depleting substances such as chlorofluorocarbons, CFCs, and halons emitted by human activities have thinned the stratospheric ozone layer, forming an Antarctic ozone hole and leading to an increase in ultraviolet rays. This UV enhancement not only increases the risk of skin cancer, cataracts, and compromised immune systems, but also threatens the health of crops, marine plankton, and the entire food chain. Fortunately, the international community has adopted the Montreal Protocol, which limits the use of ozone-depleting substances and promotes the application of alternatives such as HFCs, HFOs, ammonia, etc. This allowed the ozone layer to begin a gradual recovery, but repairs would still take decades due to the long life of CFCs in the atmosphere. This process reminds us that human activities have a profound impact on the Earth's atmosphere, and scientific discovery and international cooperation are key to protecting the environment. While human technology brings convenience, it can also cause long-term harm to the environment. The success of the Montreal Protocol demonstrates the importance of global cooperation, demonstrating that environmental problems can be mitigated or even reversed if humanity is willing to act. Each of us should also raise environmental awareness, understand the hidden sources of pollution in our daily lives, and reduce the damage to the ozone layer and the atmosphere from the details of our lives. 1. Reduce ozone-depleting substance emissions. O. Avoid using older refrigerants and aerosols that contain CFCs. O. Promote low-impact alternatives such as HFOs and ammonia. 2. Raise environmental education and awareness. O. Popularize ozone layer protection knowledge and raise public awareness of sun protection and environmental protection. 3. Strengthen international cooperation and monitoring. O. Continuously monitor the recovery of the ozone layer to ensure that countries comply with the provisions of the Montreal Protocol. O. Encourage the research and development of safer and more environmentally friendly industrial and household chemicals. 4. Personal daily actions. O. Energy conservation, emission reduction, and chemical waste. O. Prioritize environmentally friendly home appliances and refrigeration equipment.